So the last part of this unit is graphing exponential functions and then also graphing log functions. We haven't talked about logs yet, so that'll be a whole different thing. But the reason we're doing exponential functions and logs in this unit is because they're inverses of each other. Okay, and we've been studying inverses lately, right? And so that's the connection that we're going to make here eventually. But for now, we're just going to learn about exponential functions. Some of this should be review. In case you forgot all your properties of what you can do and what you cannot do with exponents, here's a table for you. There are some certain things that you should be able to do without a calculator. Okay. For example, this one, what do we do with a negative exponent? So it's 1 over 2 to the 4. And then if you don't know what 2 to the 4 is, you should be able to quickly figure it out, right? 2 times 2 times 2 times 2 is 16, so we get 1 over 16. This is a nice little review right here. The fraction exponent. Do you guys remember what the denominator means?
The power you put in front of the root.
It's the index. So this is a cube root.
Wow.
Look familiar?
No.
3. Nice.
And that's to the second power. Remember doing those last semester? Okay. What's the cube root of 27?
3.
And then square it?
9.
Pretty easy, right? What about 23 to the 0?
1.
Okay. Any questions on that? Okay. Take 10 seconds and do these with a calculator. Let's just make sure we can type these in correctly. You'd be surprised. Sometimes you type something in wrong and you get the answer wrong on a test because you don't know how to press buttons. But let's round to 2 decimals here, okay?
An extra practice packet or no packet.
For this class?
Yeah.
Yeah.
What did you go to?
Oh, second, the division symbol. What? Yes, that will. I just put that in 20. You did put that in 20. Yes, you did. It's second and then the division. Yeah.
Never heard this.
Oh, welcome to the club. We never heard of it.
What is E?
2 decimals is fine. If you've done this correctly,
Nice.
you should have gotten this.
Yes, sir.
So right here, above the division symbol, it's kind of hard to see on this calculator, but you guys should see a blue E. Okay? And then you type in the exponent. Now, I also want to point out, okay, something, since we're talking about inverses, right? We've been dealing with inverses this unit. Just want to point out how your calculator is laid out. This button right here is the squaring button, right? In blue, what do you got? That's because they are opposites or inverses of each other. Okay? You don't know this yet, but right here where you see log, above it it's 10 to a power. We're going to talk about those. Those are inverses of each other. Okay? Here's where you finally see the other E. You guys haven't seen E too much. We'll talk about what it is and all that later, but E and natural logs are inverses of each other. Okay, so that's why they're connected that way. Same with the trig functions. Sine, inverse of sine, cosine. So the calculator is laid out in that way so that it actually makes sense when you're doing the opposite of something. Okay? All right, so let's talk about an exponential function. Here's the format for it. Typically you have some constant and then a base, okay, to a power. This is very important here. This base, A, is typically called a growth factor. Okay? We want it to be positive, and we never want it to equal 1. Okay, and there's a few reasons for that. First of all, if we have C So y. Let's say we have c and then 1 to the x. Well, what's 1 to anything? So this is really just, and that's just a horizontal line. Okay, exponential functions are not linear. Okay, so that's why this cannot be 1 for the base. And we don't want it to be negative either. Okay, because if it's negative, what's going to happen is you'll start to bounce around between positive and negative numbers, and it's not really a continuous function anymore. Okay, so you just need to remember that this value here is going to be positive, and then that's it. Okay? This value, c, is usually the initial value, unless there's other variables going on. And you'll see how that affects the graph momentarily here. Okay? Very easy to remember this. The domain for exponential functions is always all real numbers. Okay? Reason is exponents can be anything. You could have negative exponents, you could have 0 exponents, you could have positive. It doesn't matter what it is. Exponents can be anything. So that's why the domain is all real numbers. Okay? We'll talk about this in a second. Let's just look down here at example 2. Okay? Here we have a column labeled L test, which L stands for linear, by the way. And E is going to stand for exponential test. Okay? If we're looking at this table, do you notice any patterns as we increase the x values by 1? What's going on here? Going down by 3 each time? So, in other words, negative 3 is the what of the function? Because this is going up by 1s, right? If I do negative 3 over 1, negative 3 over 1, that's like rise over run, right? So this is the slope, okay? So to check if we have a linear function, if we have a table, as long as the x's are going up by the same amount, if we see that the y's are going up by the same amount or going down by the same amount, then we know it's linear, okay? This one, if we go to the second table, first we're going down by 16, and now we're going down by 8. So right away, I'm going to say this is not linear.
So you can't, it has to be a positive and,
Adding or subtracting this by the same amount to be linear, yes. But as far as what's really happening, and you said it already, what's going on to get to 16, to get to 8? So this is really, if you divide, you get 16. If you divide by 2 again, you get 8. Divide by 2. Okay, anytime you can divide by the same number or multiply by the same number, that's the exponential test right here. So if we go back over here, okay, this is kind of written in a funny notation, but all this means is, for example, like y2 divided by y1 is going to be the same as y3 divided by y2, y4 divided by y3. In other words, if I do 16 divided by 32, what is that? Other way. 16 over 32 is a half. What about 8 divided by 16? Half. So that's what they mean there. Okay? Same thing with 2 and 4. So that's how we can tell by looking at a table or data if we have a linear or if we have an exponential graph. Okay? Any questions on that? Okay, let's turn the page. Here's a review for the rules of shifting graphs and translations. We've done all this before. I'm not going to spend time teaching it again. If you forget how things work, here's a nice little summary for you. What I do want to focus on now is the graphs of these exponential functions. Okay? And this is actually a very important thing right here. Unless there's a shift, up or down, these 3 points will always be on your graph for every single exponential graph. Okay? And this is always your asymptote, unless there's a shift up or down. Okay, and you'll see I'm just going to go ahead and get right into it here. If I just do this graph by hand, you'll kind of see what I'm talking about. Now, we'll have the calculator available, so you could always use that to double check. But if I was doing this by hand, okay, let's start with 0. If I plug 0 into x, actually, let me make a little table off to the side here. If I plug in 0, y is definitely 1, right? Well, what if I plug in 1? 2 to the first is 2, right? Let's go one further. If I plug in 2, what do I get? 2 squared is 4. And you can see right there in the table, you got that relationship, right? 2 over 1, 4 over 2, everything's doubling, okay? Now, let's go backwards. So if I go to -1, 2 to the minus 1, how do I figure that out? You make it a fraction, so it's 1 over 2 to the 1. In other words, 1/2. So now over here, we get closer to 0, right? Now if I do -2, instead of 1/2, it'll be 1 over 2 squared, which is 1/4. So now this gets lower, but not closer to, or not 0, right? What's going to happen if I keep going backwards here? Closer and closer to 0, not ever equal to 0, right? And that's why we have horizontal asymptote. Okay? And so your graph is a nice smooth curve that looks something like this. Now, do you need this many points when you're graphing on a... No. I'm just showing you that so we can see the shape and so we have a good picture. All I would really care about is that you have 3 points. And you can use your calculator if you want to save you the hassle of doing it by hand. Let's do this one right here. Oh, and here are the 3 points. These 3 right here. These are the 3 that we're talking about that are always on the graph. Okay? You see what the A value is here? The A value is 2. So automatically I have 1 over 2, 1, and then 2 as the y values for those points. Does that make sense? So over here, if I'm doing this by hand, at -1, 0, and 1, what should my values be? 0, 1 is one of them. And then 3 over here. And what about over here? 1 over 3, right, 1/3. And this is all I need. You guys okay with that? Yeah. Okay. Now on the calculator, again, this isn't horribly difficult. You just type it into y equals, okay? And you can look at a table, and you can see right away that things get really big really fast. So I should probably go back. Here are the points we're talking about right here. Okay? -1 is 1/3, 0 is 1, 1 is 3. Okay, so if you forget how to do it by hand, I mean, it's here. There's no reason that we should get any of these incorrect as far as the picture is concerned. Does that make sense? Okay. Go ahead and get a sketch for this real quick. If you want to use a calculator to get those 3 points, do it. Oh, I forgot my asymptote here. Yes. Mm-hmm.
Is the asymptote always going to be y equals 0?
Yes, unless there's a shift up or down. If everything shifts up, the asymptote will shift up with it. What's the one point on this graph that is the same as all the other ones? 0, 1, right? Now, if you don't really know what E is, but your calculator tells you when x is 1, what is our graph? 2.718, right? So it's close to 3. And that's, for now, that's great. If you can just remember E is a little less than 3 for now, that's good. So 1, 2, 3, just a little bit under. And then now if I go to -1, should, so something like this, right? Still have an asymptote at y equals 0. Okay. All of these look the same. Okay, and there's a reason for that. These values right here, the 2, the 3, the E, these are all where A is bigger than 1. So all these graphs will be increasing. Okay? If we flip the page real quick and look at something like C, here now we have A is less than 0. Okay, we still have a positive, which is a requirement, but, oh, sorry, what do I mean? Not less than 0. It's less than 1. It's still positive. It's less than 1, though. If you take a look at that graph, what happens? It flips, yeah. So instead of having something that looks like this, it flips over the y-axis, and now it's decreasing, okay? And I can show you either using a graph or, remember, 1/2 is really the same as 2 to the -1, right? And this is the same as 2 to the -x then. Do you guys remember what happens if there's a negative in the x? Thinking of those rules of symmetry or translations that we learned? It flips over the y-axis. Okay, so it's not a coincidence. It's still following all those rules that we learned. Okay, but now you just need to remember, if you see a fraction less than 1, your picture is going to be the reverse. Instead of going up, it'll be decreasing. Okay? Actually, let's finish this example. Still, though, what point is on the graph? 0, 1. And now at 1, I'll be at 1/2. And at -1, I'll be at 2. So now we have something that looks kind of like this. Okay? I don't really have many more notes to do. I want you guys to have time to work in class. But I do want to fill in now the domains. Actually, we'll go back and do one more after this, but we'll do D here in a minute. Let's just go back in and fill in all these details, okay? What is the domain for all 3 of these graphs here? Good, so either writing down all real numbers is fine, or if you want to use interval notation, that's cool too. What was the range for all 3 of these? Does this ever go below? It doesn't cross what value? It doesn't cross 0. It never equals 0, right? So how do I write that in interval notation? We use a parentheses for 0, and then infinity is still good for the, because this keeps going up forever, right? Any x-intercepts? No, if it doesn't equal 0, this is not going to have any. Same all the way across. Do you guys see, though, that if these shift down, now we're going to have x-intercepts, right? Okay, so be aware of that. What's the y-intercept for all 3 of these? 0, 1. Again, if that shifts up or down, that'll change according to the rules. And what was the asymptote for all 3 of these? Good. Okay, is this making sense, these new graphs? Okay, then let's just finish with example D. Let's do that one together, and then you guys will have a chance to work on the packet or get a head start in Math Excel, whatever you guys want to do. Okay? Why don't you guys try it first? Okay? Get a picture first, and then we'll go ahead and do the details together. I know we're getting pictures with the calculators, but just to make sure you guys remember, that's so tiny. Okay. There are two major shifts, right? If we think of the parent graph here, the parent graph is 2 to the x, right? What does the plus 1 do to this 2 to the x graph? It goes left 1, and now outside we're subtracting 2, so everything shifts down 2. So if you look at your calculator, it should be this exact picture we started with, just shifted left 1 and down 2 units. Are you guys seeing that? Okay. And so when I graph this value over here, you guys, if there's ever a minus or a plus over here, that tells you the up and down, and it's going to change the asymptote. So instead of being at y equals 0, where's the asymptote for this? Very good. And I would always start with those. Okay, just draw the asymptote on there as a reference. Okay, and then now you can use the calculator, or if you remember your rules, you can shift everything. Let's see. What are some points? 0, 0. Negative 1. Negative 1. 1 and 2. And if you want more, but these three are fine. Just make sure you have this shape here. Yes.
Wait, is it one, that top point? What is it? 1, 2? Yeah.
Mm-hmm. So what's the domain? All real numbers still. What's the range? Careful.
No, -2.
Yeah. It shifts down, so now instead of 0 to infinity, it's -2 to infinity. Now this is kind of nice. Oh, but I'll just fill this in too. That's y equals -2. This is kind of nice because we can see this x-intercept. It's really easy to, it's just 0, 0, okay? But I do want to point out, because this is something you'll have to do eventually, whether it's in this section or in the later sections, how would you find the x-intercept? You let y equal 0, right? So if you put 0 into y, you have 0 equals 2 to the x plus 1 minus 2, and then you can solve this equation. This is a sneak preview what we're going to be doing later. Add 2, right? And we really haven't done these yet, but yeah, we don't want to think of it that way. Let's just do an intuitive approach. I mean, technically you could take the x plus first root of both sides, but that's strange and we don't know how to do that, right? Here's how we can think about it though. What exponent would keep a 2 as a 2? So this needs to equal 1 right here. And the only way that equals 1 is if x is 0. Does that make sense? So that's how we can confirm algebraically that our x-intercept is 0. And then to find the y-intercept, you would do what? Plug in 0 for x. If you plug 0 into x, okay, 0 plus 1 is 1, 2 to the first is 2, 2 minus 2, also 0. Okay, if you have a good picture, easy to do. If it's not quite where it looks like it is, you can do algebraic techniques and still get the same answers. Okay?